All right, today I wanted to go over a pretty fun result from matrix theory um, using things like block matrices, the Jordan form, eigenvalues, the trace of a matrix, the determinant of a matrix, some basic analysis with power series expansions, and most importantly, the idea of exponentiating a matrix or raising specifically E, Euler's number, to the power of a matrix. So, translating e to the x to e to the a, where a is a matrix, and how we can do this in matrix theory. So, I'll get straight into the problem, but I would just say that as a prereq for this video, which of course isn't necessary, you can enjoy this, I think, either way. A pretty good foundation in basic linear algebra, and vectors, and basic matrix operations, as well as basic understanding of eigenvalues, as well as some basic analysis just from like calculus 2, just the idea of expanding something with a power series, Taylor series, whatever. And as far as proof techniques go, this is really just a proof by definition. We're just going to derive a pretty cool result that it just naturally shows up from the definition of these things that we're going to be talking about. We'll just use some basic deduction along the way and call on some other definitions from algebra and linear algebra. And so if you're interested in those, I would say look up more resources, or maybe I'll make a video on them sometime, but I won't have time to explain everything, mainly upper triangular matrices, but we will be relying on them for this proof. So the big idea of this proof is that we're going to use what's called the Jordan normal form, or the Jordan form, or the Jordan canonical form of a matrix. All words to describe the same thing. I'll just use Jordan form because it's easiest, but if I accidentally interchange them, I'm talking about the same thing. So the details of what the Jordan form of a matrix is, what this decomposition represents, isn't entirely necessary for this video. It is a very fundamental part of linear algebra, specifically with what we call spectral representation theory in matrix theory. But you won't need to know how to specifically derive the Jordan form of a specific matrix. We're just going to be dealing with arbitrary square matrices. And even to make it simpler, I'm just going to assume that all the entries are complex. So they're just in the field of complex numbers, n by n. So how do we define this? Well, we're going to start with what's called a similarity transformation. If you hadn't heard of this, we say that a matrix A is similar to B, using this squiggly, this tilde, if there exists some matrix P that is invertible. So just any arbitrary matrix P that's invertible. What is this? Such that B equals P inverse AP. And this is what our similarity transformation is. So it really just boils down to a matrix decomposition. So now, what is a Jordan form? So, well, let's first lay out the problem. So we'll say this is a problem. Show that for all square complex matrices A, so all matrices A in the field of Cn by n, A is similar to J sub A, where J sub A is the Jordan normal form. I'm just going to say this. JNF or JF or JCF, Jordan form of A, where J sub A is this matrix formed by the diagonal of the Jordan, what we call the Jordan blocks, and the eigenvalues of the eigenvalues. So this will go up to just like K or something. Okay, so this is the first part of the problem. So we want to show that for all square matrices A, this can be arbitrary for Jordan form, but we're just going to assume they're complex just for sake of notation, that A is similar to J sub A, where J sub A is what's called the Jordan normal form of A, where we define J of A, this matrix J of A, as a diagonal matrix with what we call the Jordan blocks of the eigenvalues in the diagonal, and then ones in the super diagonal. And I'll draw this matrix out later so it makes more sense, but this is how we concisely define it. And if you're confused on what Jordan blocks are, or you've maybe never heard of blocks, we're going to be using these things called block matrices, which is fairly intuitive. It can get tricky, but I'll just say this. We can have a matrix A, and we can, instead of putting elements up here, here, and it's a big matrix, we can concisely represent those elements of the matrix as sub-matrices of the matrix itself, thus becoming a block matrix. So our original matrix is A, and we can say that all these elements in the top left here are another matrix itself called B, and these elements are C, and these elements are D, and these are E. And this might be a block matrix, a 2x2 block matrix, where B, C, D, and E are themselves matrices. Now there's a whole bunch of results from this, mainly with formulas of determinants and LU decomposition and all this stuff that you could do in numerical linear algebra. But this is just all I would think about. It's just this idea of blocks is just matrices inside of matrices. That's all it is. And so in this case, J up here, those are blocks. This is what we call the Jordan blocks. So you can think of those themselves as matrices inside of a matrix. All right, moving on. So this whole statement up here is part one. And what we want to do is use the above fact. And the above fact that we're showing is essentially just the existence of the Jordan form to show that the determinant of e to the a is equal to e to the trace of a, denoted tr of a. Now, this is sort of the fun part of the proof. Like, okay, how did e get there? And yes, that is Euler's number. This isn't like the standard basis vector. This is Euler's number e, 2.718, blah, 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 blah. And this idea of trace, which you might have not seen before, and then the determinant, which you probably have seen. And what we're really going to get down to, I think, by the end of this result, which is really cool, is, you know, this idea of representing the product of powers as the sum of powers. Essentially, in algebra, you know, if we have a to the x, let's say, you know, a to the x, a to the y. This is the same as saying a to the x plus y, where a is, you know, the same base. And this is exactly what we're going to be deriving, essentially. And it might not make sense now, you know, how does this formula up here relate to that? But it really does make sense, because we'll get down to it that the determinant sort of expresses things as multiplication, and the trace of a matrix expresses things as the summation of the diagonal elements. But I think I'm getting too far ahead. So this is our end goal. So this is really what we want to show. The Jordan form in this case is sort of just going to be used as it's just a predecessor, because what ends up happening in this proof is that if we can boil this matrix A down into a upper triangular matrix, then this proof becomes a lot simpler. And J sub A, the Jordan matrix or whatever, is an upper triangular matrix. And if you haven't heard of that, what an upper triangular matrix is, I'm going to define it now. and all the nice properties it has. So what is the big idea here? So we are going to define this with a similarity transform, which means that we'll say for every square matrix A in Cn by n, there exists, so let's say this, for all A in Cn by n, there exists an invertible matrix P, this is the big picture, and a matrix J sub A such that J sub A equals P inverse AP. And what is this saying? Well, really, we're just saying that A is similar to this matrix J sub A. And this is a very fundamental result. Any arbitrary square matrix has a Jordan form. This is the the big existence theorem of and uniqueness theorem of Jordan form. And so we're really just going to rely on this. So what else can we say? We can also rewrite this as A equals PJA P inverse. Of course, we want to explicitly define that this is okay because, matrices don't generally commute, but this is okay. We can just rearrange the terms to get this. So these two are equal to each other in this case. So since the complex numbers are closed algebraically, which is what we say, and this is derived, if you're wondering, from the fundamental theorem of algebra. So this idea of the roots of polynomials, having complex roots. This is why we say C, the complex numbers are algebraically closed, and we define something called the characteristic polynomial, which you've probably seen if you've ever calculated eigenvalues. And so we generally define this as P sub A, so the characteristic polynomial of a matrix A of the values lambda is the determinant of the matrix A minus the scalar multiple of lambda times I, where I is just the identity matrix. And while we're not calculating eigenvalues explicitly right now, we know that the determinant itself is defined as the product of something. More specifically, the determinant, so let's just do some little background right here so the next step is clear. The determinant is a function that maps a square matrix to a scalar. So that is the determinant of any matrix yields a scalar. So the determinant is a function from, let's say, M of just with respect to some field. So M sub n is just going to be the set of all square matrices, and it just yields some scalar from that field F. So it assigns each matrix A and M sub n of F to a scalar determinant of A. And a common definition that we use for this is, I believe it's Leibniz's definition of the determinant. The determinant of A is, let's see if I remember this. It's the sum for all permutations sigma in some what is this? The symmetric group Sn of the sign of that permutation sigma times the product, capital Pi, of the piecewise elements A sub I and with respect to the permutations I think. So all that we really want to look at, though, is just this. This is the big idea. We essentially define the determinant as a product of elements. In this case, S sub n is what we call the symmetric group of all permutations 1 through n. And then the sign of sigma is what's called the sign, or I think sometimes the parity, not parity, but parity of the permutation sigma. And then A sub I are just the entries of, sorry, I said piecewise elements, but they're just the entries of the matrix A. And that being said, all we need to know is that the determinant takes a matrix, a square matrix, and it poops out a scalar f from the field that the matrix was a part of. And we define that determinant with the sum of the product, but specifically we're focused on the product. That's why we say that the determinant is defined by multiplication, and the determinant has multiplicity, algebraic multiplicity, which is something we'll use later. Okay, and if you're wondering what permutations and signs are, this is just this is like take an algebra course, an abstract algebra course. This doesn't matter in this case, but I wanted to try to be as explicit as possible, thinking it would help. So now we'll go to the next result and why I think this is helpful. So we had our characteristic polynomial, which is the determinant of a minus lambda I. And so if we rely on the fact that the determinant is defined by multiplication like we just found, then the expansion of this is pretty simple. It's just the product of lambda minus lambda 1. So this is the factorization of this to the power of, let's just say, m1. And this goes on and on and on to just lambda minus lambda k, eb sub k, where lambda 1 through k are, of course, the eigenvalues of A. Okay, so this is what we want to remember for if we were to expand this formula for the determinant of A minus lambda I for the characteristic polynomial. We're essentially just taking this product of the difference of eigenvalues. And an important thing to note is that we order eigenvalues based on their singular values. Actually, scratch that. Like I didn't say it. That doesn't matter here at all, really. Actually, that's sort of just implied. So what we want to do now is to further define this is consider the eigenvectors associated to the eigenvalues lambda. But of course, we're not doing this example on a specific matrix. We're doing it generally. So how can we sort of talk about those? So I want to define what's called the generalized eigenspace. So for each eigenvalue lambda, specifically lambda I, because it could be any of them, we'll define the generalized eigenspace as just some set. I'm just going to call this set gamma. So the set gamma with respect to our eigenvalues lambda I is the set of all vectors v in Cn such that A minus lambda sub I times the identity matrix. And now we want to consider our factorization from earlier. So we're just considering this for all powers of R in this case. We'll just say R times that vector v is equal to 0. And of course we want to make sure that R in this case is just greater than or equal to 1, because if it's 0, it's just trivial. And we want to also assume that v is not equal to 0, because that's trivial as well. And you know, this might be sort of a more abstract generalized definition, but if you've seen eigenvalues, you've probably seen, you know, AV equals lambda v. This is how we find our eigenvalues and eigenvectors. So all the formulas for the determinants for eigenvalues come from this. The idea is that we're taking a matrix vector product and it's breaking down into just scaling a vector v with some scalar lambda. And we can see that here. We just have A minus lambda I times I is our matrix times v equals 0. So our eigenspace is the zeros of all of those computations. Thus why we set it equal to 0. So hopefully that makes just a little sense. Now, what we can show essentially that I will not do here is that the basis Cn, so the vector space Cn, complex vectors, is the same as the direct sum, what we call the direct sum of everything in this set. So this generalized eigenspace essentially implies this. So we're saying that Cn, this vector space, is what we call the direct sum. Let's just go from 1 to k of this field that we just defined. Or sorry, this set that we just defined. And this is the big result that we're using here. Now, what is this saying? If we choose a basis, so this set of vectors, that consists entirely of generalized eigenvectors given by a minus lambda I times I of r times v equals 0, which exists, of course, for each lambda I. Obviously, that's implied. Then we can obtain a basis for Cn defined by the direct sum given above. Now, the direct sum, I might make another video on it and how we define projectors and stuff like that. But as I was saying, we really just want to get through this so that we can go on to the real proof. But I might make a video deriving this formula explicitly. So now we've essentially just shown that there exists a Jordan decomposition, or I mean a Jordan form, excuse me. So with this basis, we can say that the matrix representation of A becomes what we call block diagonal, with each block being a Jordan block that corresponds to an eigenvalue lambda, and that a Jordan block of size m is of the following form. So if none of that made sense, then we'll just draw it out what our Jordan matrix looks like. So J, with respect to our eigenvalues, lambda, is the following matrix. So we have lambdas all in the diagonal. And this goes just further down to lambda. Actually, I'll leave even better than that. This is all 0. This is a 0 block. So you can consider this all zeros below the diagonal. And then we have ones in what's called the super diagonal, or maybe it might be called the upper diagonal or something. And so these go all the way down to here. So basically above the main diagonal, which is lambda here, there exists another diagonal of just ones. And this is why this matrix is said to be diagonal, but not strictly diagonal, is what you might hear. And then, the rest here are just zeros as well, so 0 blocks. Okay, so this is our matrix. And this is the matrix that we want to rely on for the rest of this proof. So if you can't tell already, this is an upper triangular matrix, meaning that we have elements only in the diagonal and above the diagonal, and everything below the diagonal is equal to 0. That's what an upper triangular matrix is. Something like this. Hence being upper, because there's only stuff in the upper. And there's lower triangular matrices, and you can, I'm sure, find out where that is. This just flips. There's only elements below the diagonal. Now, the reason we want to use upper triangular matrices is that for any upper triangular matrix, the determinant is simply just the product of its diagonal entries. Now, in the Jordan form that we've just found, these diagonal entries are just the eigenvalues of A. So we'll use this fact in a little bit to further talk about e to the A. But it'll essentially just to reduce some multiplying the eigenvalues. And then the trace is defined as the sum of the diagonal. So similarly, the trace of an upper triangular matrix is just the sum of its diagonal entries. And so since the Jordan matrix only has eigenvalues along the diagonal, the trace is just the sum of these eigenvalues. So by using this Jordan matrix, we have an upper triangular matrix, and we know that the determinant of that matrix is just the product of its eigenvalues, and its trace is just the sum of its eigenvalues. Now, let's use this to prove the second part. And just so we're clear, this is it. Yeah, this is the result for the first part. We just wanted to show that there exists a Jordan form of a square matrix A. And that's what we've done just based on some basic definition and relying really on definitions of algebraic multiplicity and the fundamental theorem of algebra and this idea of generalized eigenvectors forming an eigenspace. So now, if that was sort of too boring and sort of just theoretical, let's actually do some algebra, some actual derivation. So we want to show now that the determinant of e to the a is equal to e to the trace of a. Now, if we're thinking about matrices, we know there's some operations that are well defined that you'll learn in a first year linear algebra course. We can add matrices, we can multiply matrices, but of course they don't generally commute. We can subtract matrices, but we can't divide matrices. This isn't an operation that we've defined. And when you think about it, it doesn't make sense. The idea of dividing a matrix into another matrix doesn't make sense. The idea of multiplying does, because it's not defined as scalar multiplication. We've strictly defined it by, the elements of its row and its column. And of course, we can express that even more rigorously. But now we're looking at e to the a. And this might be just confusing at first, but it doesn't take long to see, this does make sense, because this is just exponentiation, or exponentials, whatever, raising something to a power. And this makes sense for a matrix. A matrix A to the 1 is just A. What if we square a matrix? Well, it's just A times A, and multiplication is well defined. A times A times A. This all makes sense. So this is what we are going to be using. And because the exponential is well defined, we can use power series. So let's recall that, well, first of all, we have our Jordan form. We've shown the existence. J sub A is P inverse AP, or A is PJA P inverse by some rearrangement. So this is our existence that we're using. Let's recall that, in Calculus 2, we learned that e to the x can be defined by the power series. N equals 0 to infinity of just x to the n over n factorial. So we can now directly expand this to matrices. Specifically, we're considering the matrix E to the A, and this is just the sum from, let's use a different index, k equals 0 to infinity, of the matrix A to the k, so that looks kind of sloppy, A to the k, over k factorial. So this is a really cool translation. This should be very intuitive, and the fact that we can do it is pretty cool considering that we're dealing with matrices, which of course are way different than scalars. And so now we want to let's just reconsider. We have A equals P J A P inverse. So how can we fit this new idea of raising a matrix to its power and consider this decomposition PJ P inverse for any power of A that we'll call k? So this would be A to the k equals P J sub A to the kth power of P inverse. This is what we want now. So if you're wondering how this is the case that we get that formula, why is it that, this nice expansion only affects J in this case? It seems like P and P inverse are untouched. Well, we can sort of just look at this a little bit. So if we just consider e to the a, this is just 1 plus a squared over 2 factorial plus a cubed over 3 factorial, so on and so on. Now, this is just, you've probably recalled as the definition for e to the x, the expansion at least, using Taylor series. But let's be very explicit and ensure that since we're dealing with matrices here, 1 is a matrix. So how do we represent 1 as a matrix? Well, it's just I. It's the identity matrix. So in other words, this is I plus a squared over 2 factorial, on and on and on. Okay, now we know that A in this case is the same as PJ P inverse, where J is the Jordan matrix of A. So because A is PJ P inverse, this implies that e to the a is the same as e to the PJ P inverse, which is really just I plus PJ P inverse plus PJ P inverse over 2 factorial PJ squared plus PJ cubed P inverse over 3 factorial plus on and on and on up to K or N or whatever. So one thing that we can notice about this expansion is that we start with I. This is essentially just a scalar. We could just think of it that way. This is just the equivalent of 1. And then in every term on and on and on, we have, we're dividing by 2 factorial, 3 factorial. That's just a scalar. So we can pull that out anytime we want. But every single time J is encapsulated by P and P inverse. You have PJ P inverse, PJ squared P inverse, PJ cubed P inverse, on and on and on. So we can sort of rewrite this as P times the identity plus J squared over 2 factorial plus J cubed over 3 factorial plus on and on and on. And then on the other side here we have P inverse. Now, what we're getting to next is, of course, we've already stated above that a to the k is PJA to the k times P inverse. Now, what is this inside of here? So we have P on the outside, P inverse on the outside. What is this? Well, this is just E. This is just how we defined the normal Taylor series for e to the a. 1 plus a, except here in this case, a is J, the Jordan blocks. So this is just e to the j. So that gives us P times e to the j times P inverse. And this is what we want. This is what we're going to move on to next now. Pretty cool, right? So essentially, if you haven't noticed so far, it seems like exponentiating A and exponentiating J are really just the same thing. And that will play a big part now. So we can be, just before we move on, I'll write up here what we just did, just to summarize so we can look on e to the a, just the sum PJ P inverse over K factorial. We pulled out that P and we just looked at the inner sum. 0 to infinity of J, considering all powers of K, over K factorial times P inverse, which came out to P e to the j P inverse. All right, great. So this is what we have found for e to the a. All right, let's put a here, e to the a. Okay. So what can we do with this now? Well, what we want to remember that we're looking at, let's just look at the left-hand side of the equation that we want. We're looking at the determinant of e to the a. Now, we talked about the determinant, or no, sorry, I talked about the trace. No, I did talk about the determinant. Shit. The determinant takes some square matrix in a field and outputs a scalar of that field. And because of that, we have multiplicity, essentially that the determinant of ABC, these are matrices, is the determinant of A times the determinant of B times the determinant of C. This is what we mean when we say multiplicity. And so we're going to use this for the fact that e to the a is p e to the j, P inverse. So this becomes the determinant of p e to the j, P inverse, which is the same as the determinant of p times the determinant of e to the j times the determinant of P inverse. Now, we're only really interested in the determinant of e to the j. So how do we get rid of the p in this case and the P inverse in this case? So if we considered the determinant of p times P inverse, let's just ignore the e here. This would just be the determinant of p times the determinant of P inverse. All right, now, since p is invertible, going way back to our initial definition, we know that the determinant of P inverse must equal 1. Why? Well, invertible matrices have the property that that themselves times their inverse equals the identity matrix. Now, the determinant of the identity matrix is just 1. This might be a fun proof on its own time, but this is a very well-known result. The determinant of the identity matrix is equal to 1. So the determinant of P inverse is the determinant of I is just equal to 1. And we can then conclude that the determinant of P inverse alone is equal to just 1 over the determinant of P. By definition. Because if we have, it yields a scalar. So as long as we're in the determinant, we can, do some basic algebra on these matrices and take the inverse. And if we do that, we get that it's 1 equals 1 over 1, 1. So we just get 1. So even though for matrices P1 is not the same as 1 over P, we can find this product. We can find this property, that the determinant of P inverse is equal to 1 over P. And that, we'll now use this up here. So I'm losing space again, so let's rewrite what I had. So I had the determinant of e to the a is the determinant of P e to the j P inverse. Thus, this is just the determinant. This is the determinant of P times the determinant of e to the j times the determinant of P inverse. Determinant of P inverse is 1 over P, so we just get that we're looking at the determinant of e to the j. Relying on the fact that P is invertible, which yields the identity formula. So what have we gotten to? Well, this is the big idea now. We've just shown that the determinant of e to some arbitrary matrix A is the same as the determinant of e to the Jordan matrix of that arbitrary matrix A. So this is a really big deal because now we can use the fact that J is unitary to further expand this determinant computation. So if we were to just look at a single Jordan block, J, and I've been just using J in this case, this is J sub A, the Jordan matrix of A, but I was just using J for simplicity, but now I'm going to use J in a slightly different way. I'm going to be considering J as a single Jordan block. So if we consider a single Jordan block J that corresponds to some eigenvalue lambda of size m, that block can be explicitly expressed by the following. Lambda times I, where I is the size m, plus just n, where n is what we call nilpotent, which in other words just means that if we raise n to the mth power, it equals 0. That's all it means to be nilpotent in this case, and has ones on the superdiagonal. So again, as we mentioned earlier, block matrices have matrices inside of them that we call blocks. So a Jordan block is a matrix inside of the Jordan matrix. So it itself has the form of a matrix and has the same form. It has ones along the superdiagonal, as we showed earlier with the general matrix. Now, one thing that's important is that lambda I and n both commute. Now, this is just based on the fact that they are upper triangular, but the fact that they commute allow us to use some basic laws of exponents, really. That's all it is. Say that e to the j, where j is just this block, is e to, what's our expression here? Lambda I sub n plus n. Now, this is just the same as e to the lambda I, e to the n. This is just e to the lambda times the identity times e to the n. If you're wondering why the identity comes down, it's because it's the identity. It's just equal to 1. So it doesn't matter if you put it in the exponent or if you put it in front of it. Either way, it's just a constant, and specifically it's the identity. So e times that will just equal e all the time. Now, we want to notice that e to the n is given by a finite sum in this case, or we can give it a finite sum. So as we showed the infinite sum earlier with the Taylor series expansion, we want to remember that n is nilpotent, so we'll express e to the n finitely as the following. So we'll start with the identity matrix that is size m plus n squared over 2 factorial plus on and on and on. But we're finite, so we just want to stop at the m-1 case. So we're looking at m-1 times or over m-1 all factorial. Great. Now, n is strictly upper triangular, and this is a reason we love upper triangular matrices. A result of the product of two upper triangular matrices is itself an upper triangular matrix. Now, this could again be something you might want to prove on your own, but we are just going to leverage this fact. So that is, an upper triangular matrix times an upper triangular matrix yields an upper triangular matrix, which means that n is strictly upper triangular, since e to the n is upper triangular with all the diagonal entries just being 1. So this means that the determinant of e to the n is just 1. Because we said earlier, we're looking at the determinant now of an upper triangular matrix as just the product of all its diagonal elements. And since its diagonal entries are all equal to 1, the determinant is thus equal to 1. Great. So where do we go now? we want to go back to our Jordan block. So the determinant of e to the j, where j is our Jordan block. So this is the determinant now of e to the lambda times the identity e to the n. And we derived this earlier, you saw. This is the determinant of just e to the lambda times the identity times the determinant of e to the n equals e to the lambda m, or e to the lambda to the power of m, sorry, times 1, because the determinant of the identity matrix is just 1, equals e to the lambda m, or e to the m lambda. The order doesn't matter here. They're scalar, so they commute. Okay. So this directly follows from what we've just shown, just with some basic algebra in the fact of determinants, and the fact that e to the lambda is itself upper triangular, or e to the n is upper triangular. Now, the trace of this matrix is defined as the sum, or the trace of a matrix is defined as the sum of its diagonal elements, generally speaking. So since J is upper triangular, its trace is just the sum of its diagonal elements, which is just the eigenvalues, and we just want to make sure those eigenvalues are scaled properly by the size of the matrix, by some size m. Sorry. So the trace then of the Jordan block is just m, where m is just some size scalar, times lambda, where lambda is the eigenvalues. Okay, so what have we actually shown now? Well, we found that the determinant of e to the j is just e to the m times lambda, or e to the lambda times m. And we found that the trace of j is m times lambda. So we can use this now to fill out our equivalency. So the determinant of e to the j is just e to the trace of j. This is m lambda, so all we need is this e right here. So we've shown that a determinant of the exponential of a Jordan block is the same as the exponential of the trace of that Jordan block. Now, we are still considering just the arbitrary matrix A, so we do just have a little bit more work to do. Now, the matrix J sub A, our original matrix, is block diagonal with Jordan blocks J1, J2 through JK, on and on and on to JK. Thus, the exponential e to the j sub a is also block diagonal. Again, because the product of two upper triangular matrices is upper triangular. In this case, it's block diagonal. So when we're exponentiating that, that's just the product over and over and over, which means that e to the j sub a is the same as j sub 1 times j sub 2 times on and on and on, which is upper triangular. So e to the power of j sub a is also block diagonal, where its blocks in this case now, instead of just being j1 through jk, would be just considered as e to the power of j1 through e to the power of jk. So since we're defining that as a product, we can explicitly represent this by saying that the determinant of e to the j sub a is just the product, capital pi, just going from 1 to k, let's say, of the determinant of the Jordan blocks, j sub I, so j sub 1 through k. Now, using the result that we showed earlier for each Jordan block, we know that the determinant of this, specifically e to the j sub I, must be equal to just e to the trace of j sub I, based on what we showed up here. Thus, the determinant of e to the j sub a is the product, capital Pi, of e to the trace of our Jordan blocks, which is just the same as saying e to the sum of the trace of our Jordan blocks. Why is this the case? Well, we just showed why this is the case. We showed earlier that we have essentially just A is this. So the product of the exponents is just the sum of the exponents with regards to one basis, A. Now, since the trace of j sub a is just the sum of the traces of its blocks, then we can also just write that the trace of j sub a is just the sum of the trace of j sub I. And that's the result that we've used up there. Now, moreover, since the trace is invariant under similarity, which means essentially that it doesn't matter what our basis is. So in this case, it'll be A or J sub A. Because it's invariant, this is just by definition. I'm not going to prove this. Then the trace of J sub A is equal to the trace of A. Now, what does this tell us? Thus, the determinant of E to the J sub A is E to the trace of A. And we showed earlier that the determinant of E to the A is the determinant of E to the J sub A. So therefore we can conclude that the determinant of E to the A is equal to E to the trace of A. And this completes our proof. Now, I think this result is fairly nice. There are other ways you could, of course, go about doing it. You could think of the determinants, or at least show the multiplicity by just going straight out cofactor expansion for just an arbitrary matrix, and showing that it just, for an upper triangular matrix, becomes the product of the diagonals. I would say if you want to hit that is probably a really good way to show that the determinant of an upper triangular matrix is just the sum of the diagonal elements. But in this case, we just did something similar, but I sort of tried to generalize a little bit more, using just this basic idea of exponents. But we could also just, you can see this from, if we just looked at e to the a again, we just considered all the diagonal elements, this would just be, what's the diagonal element here? On and on and on, which would just be e to the a, considering all the diagonal elements. And so then if you looked at the determinant, you might have the product of e to the a RR. And this would just go on again to recall that e to the trace of a is just the sum of those diagonal elements. So that's maybe a more index way to go. But what I really want to mention is that what we ended up with is showing essentially a very fundamental result of algebra, is that e to the x times e to the y is just e to the x plus y. That's what this final formula is saying. That's what this final formula is saying. The product essentially just becomes the sum with respect to the same basis. So this is why I think this proof is cool. I know this is probably a really long video, but I don't know. If you have any questions or if I messed anything up or left anything out, yell at me, I guess, if you care enough. And that's really it. So thank you.